Today. I will be offering some remarks on a new direction that my methodologic work has taken, in large part owing to a transition to attempt to study empirically well-being. That has naturally led to questions on how to measure things like meaning in life or social connectedness, which is not quite as straightforward as blood pressure. And so I've kind of moved away from former work on questions of mediation, interaction, spillover effects to psychometric measurement theory, but kind of trying to draw upon perspectives in causal inference. So in many ways, I still feel a bit of a novice at this. The literature is vast. It almost feels like I've been thrust back into a graduate school education program trying to struggle through a second dissertation. I've been blessed to be working with new postdoctoral fellow Noah Paget on these, who has an understanding of the literature that extends beyond mine, but really, again, trying to bring notions of causality into play. So in spite of kind of having published a handful of papers on this already, which I will make reference to, this should still very much be viewed as a work in progress presentation. I feel every year my thinking on these matters are rather different and have moved on and altered further. But I want to focus today on what's often taken as the central analytic tool in measure development, which is factor analysis. And I'll go through what I see as a few concrete problems with the interpretation of factor analysis as typically employed and in practice, corresponding to a few of these published papers. And so in some ways, this will be offering a critique of sorts of factor analysis. But towards the end, I'm going to turn to a rather provocative example where, in spite of these critiques, factor analysis performs remarkably well. And it sort of challenges everything I'm going to say previously, but I will try to synthesize these different perspectives to offer a reinterpretation of factor analysis and also pointing towards what else might be done with regard to the evaluation of psychosocial measures and assessments. So the basic setting we're often dealing with is that we have some sort of psychosocial phenomenon of interest, maybe social connectedness, for example, and we have a bunch of individual indicators, we'll call X1 through XD, often arising from self-report survey items, which are supposedly meant to evaluate various aspects of this underlying psychosocial construct. And often factor analysis is employed to try to assess the sort of underlying dimensionality of the set of indicators, X1 through XD. So typically we kind of try to say, well, might we reduce these 10 or 20 or 50 indicators to a smaller set of meaningful assessments? Often we want to know, can we just summarize it all in a single number? Maybe just take averages. Does one factor suffice for this? And maybe we just use the mean of the indicators as our assessment of the construct. When one factor doesn't seem sufficient, then often we try to see how many factors are sufficient. With sort of the UCLA assessment of loneliness, some of these factor analysis suggests three factors, one related to intimate connectedness, really close relationships, one related to more relational connectedness, social support, friendships, and then one related to collective connectedness, having a sense of community. So often there's interest in kind of reducing the dimensionality of our indicators. Different approaches are used to try to assess the number of factors. Sometimes chi-squared tests are used, comparing the restrictions on the covariance matrix of the proposed set of factors to an unrestricted covariance matrix. Sometimes other goodness of fit statistics are used that are somewhat less dependent on sample size than is the chi-squared test. Sometimes the eigenvalues of the covariance matrix of X are used. Sometimes the magnitude of the factor loadings that are estimated are used, sort of if the factors have at least a loading of 0.5 or the indicators have a loading of at least 0.3 on the factor, then it corresponds well. Sometimes various other rules of thumb are used. There's really no universal set of practices, but kind of different guidelines with regard to how many factors might be present. But if it seems that kind of a single factor suffices to explain the shared variation in the indicators x1 through xd, then it's often assumed that there's some underlying unidimensional continuous latent variable eta that gives rise to our various indicators, so that each indicator is given by some linear function of the factor, eta plus an error. And often it's implicitly assumed that this underlying latent indicator it somehow exists, that it has a meaningful scientific interpretation. And that it itself, whatever it is, even though we're only measuring it indirectly, it itself is causally efficacious for the outcome. If more than one factor is needed, then we typically assume that there are several of these underlying univariate, scientifically meaningful factors that exist and are causally efficacious. And so in this talk, I want to challenge what I take as this naive factor analysis interpretation. I want to challenge the notion that there are underlying causally efficacious univariate latent variables that correspond to these factors. Challenge the notion that we can identify the dimensionality of the supposedly causally efficacious factors with a single wave of data. Challenge dimensionality assessments when both positively and negatively worded items are used in surveys, which is often employed and by some considered best practice. And then offer a series of empirical examples illustrating these various issues, and then try to offer a reinterpretation of factor analysis, acknowledging that in spite of what I hope to demonstrate as these real challenges, it still can be a very powerful technique. Okay, so I'm going to walk through three problems with, I think, the naive interpretation of factor analysis. Again, if we carry out factor analysis, and by whatever criteria we're using, it seems like one factor is sufficient, then we often assume that kind of factor exists and that it gives rise to our indicators, and that underlying latent factor eta is causally efficacious for our outcome. There's something real. You might think of these, again, social connectedness, or maybe these are life satisfaction variables. How satisfied are you with life, and different questions asked in that regard. But there's something underlying a real latent life satisfaction that has causal effects on our outcomes and the way we relate to people, or how long we live. And really the kind of underlying view is that these measures that we take just arise from that scientifically meaningful univariate latent variable. However, even if the factor model fits the data perfectly, so that xi, our indicator, is just given as a linear function of that latent variable plus error, that's in principle consistent with the latent variable being causally efficacious for our outcome, maybe mortality, say. But it's also, the factor model fitting the data perfectly is also entirely consistent with the indicators themselves being causally efficacious for the outcome, and potentially each having different causal effects on the outcome. There's nothing from the factor model that distinguishes between these two possibilities. Nothing gives us that information. And so we might draw a distinction between just a statistical factor model. The factor model fits the indicators well. Might call it a basic factor model or statistical factor model. So we might distinguish that from a structural factor model. We're going to say that factor model is structural if the indicators do not have causal effects on anything subsequent, and if they are themselves only affected by antecedents through the underlying latent variable. So in other words, the factor model will say is structural if this diagram corresponds to reality, not this one, so that the indicators really are just indicators of what is scientifically meaningful. They're only affected by the underlying factor, and they don't have causal effects on anything else. It's the underlying factor that really does. So on a causal diagram, say interpreted as a set of non-parametric structural equations, the factor would be structural if there are essentially no arrows going out of x1 through xd and no arrows going into x1 through xd except through that latent eta. So one can also show then on such a causal diagram, this would imply that for any other variable on the diagram z would have to be statistically independent of the indicators conditional on eta. Once we know eta, nothing else really gives us information about x1 through xd. And this is what's typically assumed with most structural equation models using latent variables. But that assumption that the factor is structural is in fact so strong that it has empirically testable implications, even though we never observe the underlying factor. And so one can show, and I'll try to give intuition for this in a moment, that if it is the case that z is independent, some variable z is independent of the indicators conditional on eta, which we don't observe, and that basic latent factor model holds, then for any two indicators, our third survey item and our fifth survey item, say, and any two values z and z star of z, we have to have that if we look at the average value of indicator j, comparing two different levels of z, and the average value of indicator I comparing two levels of z, once we effectively scale by the factor loadings in that factor model, we have to attain equality. The intuition here is easiest to see in say like the context of let's say a randomized trial of a treatment. Let's say we randomized some treatment and we looked at the effects of that treatment on each of our indicators. If this factor model were structural, so that that treatment only affected the indicators through eta, then whatever the effect of the treatment on eta was, we would know what the effect on the indicator was. It would just be the effect on eta times that lambda 1, or the effect of eta times that lambda 2. So that if we looked at the effect of the randomized treatment on indicator j scaled by its factor loading, that would have to equal the effect of the treatment on indicator I scaled by its factor loading, because the only way the randomized treatment can affect the indicators is through eta. So it's kind of easiest to see with a randomized treatment, but applies to any variable. We could look at, say, an outcome. We could look at those who died versus those who didn't die in follow-up. And if we compared the indicator values of those who died versus didn't for indicator I scaled by its factor loading, and then looked at the average value of indicator j for those who died versus those who didn't scaled by their factor loading, we'd have to have equality there too. And that's actually the case for any variable. And so we can use these empirical implications to construct a test to evaluate whether that assumption that our underlying factor is structural, whether that's a reasonable assumption. I'm going to go through this. I've got two very technical slides, which I'll kind of unpack the implications of. But for those who are interested in the statistics, one can show that if the factor model is structural and we define parameters gamma I as the average value of indicator I conditional on some value of z, again, this could be our randomized treatment, and then let beta w be the difference in the value of the first indicator, x1, compared to looking at those with value z is w versus value z is 1, then we can actually parameterize the average value of the indicators given our external variable z as a function of gamma and beta. And then what we can do is we can effectively construct residuals looking at the actual value of the indicator versus the predicted value under our model, assuming a structural latent variable. We can estimate the parameters using generalized method of moments to then form a chi-squared test with d minus 1 times p minus 1 degrees of freedom. D is the number of indicators we have. P is the number of values of our variable z. If z were a randomized treatment and we're binary, p would just be 2. To look at whether that kind of parameterization we have that's implied by a structural latent variable is reasonable. There are a lot of technical complexities here with regard to estimation of the lambda parameters, what we can and can't do depending on whether z has 2 values or more than 2 values. If you're interested in all those technical details, welcome to look at the paper in the Journal of the Royal Statistical Society. But the basic intuition is again, if that factor is structural, then the effects of any variable on our indicators need to scale according to those factor loadings. That's the intuition, and we're just testing whether those empirical implications hold with data. So I'm going to apply this test to one of the most widely used scales in the well-being literature, probably the most widely used scale in the well-being literature, Diner's Satisfaction with Life Scale from 1985. This paper, according to Google Scholar, now has more than 40,000 citations. It's fairly simple scale, 5 items. Each is self-rated from strongly disagree to strongly agree. In most ways, my life is close to ideal. The conditions of my life are excellent. I am satisfied with my life. So far, I have gotten the important things I want in life. If I could live my life over, I would change almost nothing. So different ways of trying to evaluate satisfaction with life. Prior work reports very good psychometric properties. Cronbach's alpha is high. A single factor seems to explain most of the shared variance across item responses. And so the idea for kind of carrying out some of this work came from study we carried out looking at the satisfaction with life scale. It's in the health and retirement study data, and looking over time associations with all-cause mortality, a data set of about 13,000 individuals, mean age 66, looking at tertiles of life satisfaction in 2010 and 2012 with a 4-year mortality follow-up, controlling for a host of social, demographic, economic, childhood experiences, service attendance, various health conditions and behaviors, various aspects of psychological well-being, depressive symptoms, personality factors, sort of everything under the sun. And in spite of all this control, what one finds is those with high levels of life satisfaction are about 26% less likely to die in the 4-year follow-up than those with low levels of life satisfaction. What's interesting here, relevant for our considerations, is what happens when we look at the individual indicators separately. For several of them get very similar estimates to the overall estimate we get when we just average over them. For the fourth item, so if I've gotten the important things I want in life, association's weaker, but in the same direction. For if I could live my life over, I would change almost nothing, kind of no regrets in life. We find essentially no association here, which might make us think, well, maybe these different aspects of life satisfaction aren't related to mortality in quite the same way, despite all of these indicators being very strongly correlated with one another. And so if we apply the statistical test to evaluate the assumption that there is an underlying univariate life satisfaction latent variable that's causally efficacious for the outcome, using all-cause mortality as our external variable, end up with a chi-squared test with 4 degrees of freedom with a p-value of 10 to the minus 11. We have strong evidence against there being a univariate structural latent variable. So strong evidence that there really is no underlying continuous univariate life satisfaction variable to which these indicators correspond. Now, I don't think that means that the satisfaction with life scale is bad. It might be a perfectly reasonable way to go about assessing life satisfaction, sort of an average. If you think all of these 5 indicators it's reasonable to give them the same weight, then fine. What these analyses do indicate is that jump to the notion of there is some underlying univariate latent variable corresponding to life satisfaction, that's really what's scientifically driving things. There's strong evidence against that. And so I think these factor analytic models can obscure relevant causal distinctions. If the factor analytic model fits the data well and suggests a single factor, again, it's consistent with different indicators have differing causal effects. It's consistent with just a single indicator being causally efficacious for the outcome and all of the others having no effect at all. There's nothing in the factor model itself that's able to distinguish between those possibilities. So, I mean, I think this is a natural leap to make, that once we've done the factor analysis, there must be something real underlying these indicators that's scientifically meaningful. But that's something that needs to be evaluated, not simply presumed. And I think without that sort of evidence, we may be missing nuances. Indicator by indicator analyses may be relevant. And I'll come back to this again, but I think the reality is most psychosocial phenomena are inherently multidimensional. I think we've tricked ourselves into thinking that what we're looking at really can be adequately reduced to a single unidimensional construct. Why do we assume this? Well, I think often the factor analyses do suggest one factor, and then it's a natural leap to think that must be scientifically meaningful. It also makes analysis much easier. It's generally become standard practice in the field, and then we never look for evidence to the contrary. Whereas, in fact, we can. Once we start looking at relations with other variables, we can try to evaluate whether this is reasonable or not. And as we've done this sort of work, and I'll come back to this a bit later, with some assessments, like with sense of control in mortality, actually almost all of the indicators are very similarly related to all-cause mortality. But with others, the relationships are really quite different. With a standard positive affect assessment, they're often dramatically different. So again, I think factor analysis can sometimes obscure interpretation. So this is problem one. Unfortunately, I think it's not the only issue with factor analysis. Other problems can arise, even if there are these hypothetical latent factors. Other problems can arise if the factors themselves potentially causally affect one another. And an example I'll be turning to now is anxiety and depression. Evidence from longitudinal studies that anxiety can give rise to depression. Depression over time can give rise to anxiety. It doesn't always do so, but arguably there are causal relations between depression and anxiety, and that can obscure the results of a factor analysis as well. So again, I'm going to be assuming we've got a bunch of indicators, Y1 through Yp, now maybe multiple underlying latent factors. I'm going to be, for simplicity, focusing on the case of 2. Where, again, our indicators are given by linear function of those factors. But I'm going to now allow those factors to change over time. So at each period of time, we're going to say the factors give rise to the indicators that we have, but they may alter over time. So here would be an example of 2 distinct factors. Maybe one is depression, one is anxiety, giving rise to indicators for depression, indicators for anxiety. But what happens then if the factors themselves causally affect one another, so that depression at time t-1 affects anxiety at time t, and anxiety at time t-1 affects depression at time t? We might wonder what's going to happen to our factor analysis over time. This is the second very, very technical slide, so you're welcome to tune out for a minute or two if you so desire. I'll very quickly walk through, again, more details in the paper, and then I'll kind of unpack the implications when we have just 2 factors. But the basic result here is if we have, at each time point, factor model giving rise to our indicators at each time, but that those underlying latent factors at time t are given by a linear function of the factors at time t-1 plus a random error term where that may change over time. There might be distinct parameters for that random error over time. Then if we let B, this is our matrix corresponding to the causal effects of factor at time t-1 on factor at time t. If we let QD, Q inverse be the Jordan decomposition of B, where D is in Jordan normal form, this is kind of like a generalization of an eigenvalue decomposition where the central matrix can also have, does not just have diagonal parameters, but it can also have some ones. One can always do this with any matrix. And then we impose the following condition. So these aren't all entirely innocuous, and I'll come back to that. But as t tends to infinity, we're going to assume this process converges to some random variable. We're going to assume that the matrix B expressing the causal effects over time is invertible, and that the random error terms WT decay sufficiently quickly so that this sum converges in distribution to some normally distributed variable W star. Then, as that process tends to infinity, the indicators will converge to another factor model where the dimensionality of the factors is given by d star, where d star is the limit of d in the Jordan normal decomposition. So it's quite a mouthful. The implications in the case of just two factors are more straightforward of this result. One can show that under these conditions, that as that process plays out over time, the resulting dimension of the final factor model will only be 1 if the matrix B is the identity matrix. In other words, if the factors don't have causal effects on one another. If the matrix for the causal effects of the factors at one time on another is not the identity matrix, then over time, that process with two factors that causally affect one another will collapse into a factor model with only one factor. So that over time, we can no longer distinguish the two factors. Again, this does require some additional technical assumptions. The decaying error terms is not entirely innocuous, but might be reasonable in cases like anxiety and depression, where possibly the variation in this is greater earlier in life, and then by maybe middle adulthood, not all people, but one's more likely to be on a particular trajectory of mental health. One might think about this as wealth and income likewise can affect one another, but greater fluctuations earlier in life as life trajectories are set. So that would be kind of the substantive content of some of these technical assumptions. But again, the basic result is if we have two factors that causally affect one another, that will, under these conditions, over time, converge to a factor model with just one factor. That's kind of the bottom line with at least two factors. Things do become a bit more complicated with several factors. And interestingly, if you go through simulations, it often doesn't require that many steps before you can no longer distinguish between these. This is a limit result, but in simulations, even with sample sizes of 1,000, 3,000, often with 3, 4, 5 steps of simulating, you can no longer pull apart the two factors if the factors are causally affecting one another. What are the implications of this? Well, if there's any possibility that there's more than one factor and the factors are affecting one another, then evidence from a factor analysis with a single wave of data really doesn't tell us much about the underlying dimensionality of the constructs, because we might expect to see one factor only, even if we have 2 or 3 or 4 factors that are causally affecting each other over time. And the goal of many of these psychometric measure development efforts is trying to assess whether a single factor would suffice. But it would be very odd to be in a context where we don't know much about the dimensionality, but we were absolutely certain that if there were more than 2 factors, then they couldn't causally affect one another. That would be a strange position to be in. So it seems like if there's any possibility that the phenomena under study corresponds to 2 or more factors, and those have causal effects on one another, then factor analysis with a single wave isn't really going to tell us much if we come to the conclusion that one factor is sufficient. Is this relevant? Well, going back now 30 years, but this claim has been repeated again and again in the factor analytic literature. If one looks at anxiety and depression items and runs a factor analysis, you often only get one factor. So here's one of the earlier papers reporting on this. The abstract psychologists believe that anxiety and depression self-report scales tap distinct constructs. This assumption was tested using confirmatory factor analysis on mood data from non-clinical samples and a clinical sample. These analyses provide evidence that anxiety and depression self-report scales do not measure discriminant mood constructs and may therefore be better thought of measures of general negative mood rather than as measures of anxiety and depression per se. Fast forward 20 years, this is a meta-analytic confirmatory factor analysis using 28 different samples that all employed hospital anxiety and depression scale, kind of revisiting this question, trying to combine evidence, and the conclusion here is due to the presence of a strong general factor, the hospital anxiety and depression scale does not provide good separation between symptoms of anxiety and depression. We recommend it is best used as a measure of general distress, and claim repeated by very prominent psychometricians and methodologists. But, I mean, I think the supposed conclusion here is basically nonsense. I think the fundamental emotions underlying depression and anxiety, sadness and fear, I think are very different from one another, different experientially. And so I think what's going on here is just the fact that anxiety can cause depression, depression can cause anxiety. Evidence from meta-analyses of longitudinal studies suggesting this. And so coming up with one factor is exactly what we would anticipate if we had these causal effects. Similar phenomena, again, can arise in cases where multiple factors or multiple facets of an underlying phenomena. This will tend to give rise to a single factor, at least in some cases if the causal effects are strong enough. So we might wonder kind of how many other instances does this sort of phenomena arise. And I think this comes down to the fact that with a single wave of data, we really can't distinguish causal from conceptual relations very well. And we are very careful in epidemiology of distinguishing association from causation. We say association's not causation, and we need longitudinal data over time, or experiments, or quasi-experimental designs. We need to be clear about our assumptions in moving from conclusions about association to causation. We might say the causal fallacy is assuming that a correlation implies causation, and we're very careful in epidemiology not to make that causal fallacy. And the whole potential outcomes framework was developed to protect us from that and to help us understand the assumptions that we need to make when we move from correlation to causation. But I think the opposite error arises in the measure development literature. Much of this assumes that correlation never implies causation. It always indicates a conceptual relationship. If we see two indicators strongly correlated, then they must be conceptually related as well. And so we might call that the measurement fallacy. Correlation never implies causation. And I think that fallacy underlies a lot of the interpretation of the psychometric evaluation work. And I would argue that this measurement fallacy is perhaps as problematic as the causal fallacy. We've accepted in epidemiology that good measurement is necessary for good causal inference, but I think the reverse is also true. Being aware of causal relations is really important for good measure development. So again, I think this second problem also suggests that evidence for a univariate factor structure for the covariance doesn't mean that all indicators are assessing the same thing. These factor analysis with a single wave of data should really be interpreted as characterizing associations amongst indicators that might arise from conceptual relations, but might instead arise from causal relations. So these first two problems that I've tried to document essentially concern taking a multidimensional phenomena and confusing it with a unidimensional phenomena. Unfortunately, I think the reverse can also occur. And so my third kind of problematic example will be illustrating that. And I think this is I don't have a theoretical result. This is going to be just numeric simulation showing this issue can arise. But I think this is closely related to the use of both positively and negatively worded items on a survey, and I'll come back to that. But first I'll kind of go through the numeric example, suggesting that things might not be as straightforward as we sometimes hope. It basically relates to kind of different indicators might be assessing different parts of the distribution of an underlying univariate phenomena. So let's suppose we had 6 relatively reliable indicators of a single, now we are going to have a single underlying univariate eta. Assume that's the case, and we have 6 indicators, y1 through y6, generated by 0.9 times eta, that underlying univariate latent variable plus random error with variance 0.19. But let's suppose that in the assessment data we actually have the first 3 indicators, z1, z2, and z3, are truncated below at minus 0.05. So if they're above minus 0.05, we get the actual value. If they're below, then we just get minus 0.05. So they're truncated below by minus 0.05. And let's suppose that the other 3 indicators, z4, z5, z6, are truncated from above by positive 0.05. So the first 3 indicators are going to give us a lot more information about the latent when that latent variable is positive, and the second 3 indicators are going to give us much more information about that latent variable when the latent variable is negative. But the 6 together give us a lot of good, helpful information about that latent. And if that's the data we had, we might be able to very easily see that, the first 3 indicators are truncated below, the other ones are truncated from above. But what would happen, as is typically the case, we get effectively standardized data where we've subtracted the mean, we've divided by the standard error. It might be a whole lot less clear that this was our underlying data. So let's suppose that the data we actually observe are just standardizations of those truncated measurements. We'll call that x1 through x6. Again, still, if we knew what was going on, still quite informative about the underlying latent. What happens if we employ factor analysis here? And remember, there is in fact only one underlying univariate latent variable here. We're simulating it. What happens if we apply factor analysis? This is simulated data with a sample size of 1,000. Well, if we consider whether one factor is sufficient, then under the null hypothesis that one factor is sufficient, we've got 6 factor loadings for each of the indicators. Compare that with an unconstrained model for the correlation with 15 parameters. The likelihood ratio test, 9 degrees of freedom, gives a p-value of 10 to the minus 306. So strong evidence that one factor is not sufficient. What happens if we consider a 2-factor model? Well, things turn out, what we would often interpret very, very nicely. The first 3 indicators load strongly on the first factor, and the second 3 indicators some moderate weakly on the first factor. And then for the second factor, the second 3 indicators load strongly on the second factor, the first 3 indicators quite weakly. So kind of numerically, things look pretty good for 2 factors. If we do a chi-squared test, likelihood ratio test whether the 2-factor model is sufficient, we get a p-value of 0.88. We'd say, well, look, the 2-factor model is good enough. It looks like we have 2 distinct factors. But the actual variable generating this data is univariate. And I think this sort of phenomena, in fact, happens pretty routinely whenever we're using positively and negatively worded items. I think what these items are often doing is essentially assessing different parts of the distribution. So to illustrate it, these are the 6 items in the life orientation test revised. This is a standard assessment of optimism used in thousands and thousands and thousands of papers. I think for a generic assessment of optimism, my view is that it's pretty good, but first 3 items are positively worded. I'm always optimistic about my future in uncertain times. I usually expect the best. Overall, I expect more good things to happen to me than bad. And then the second 3 items are negatively worded and reverse coded. If something can go wrong for me, it will. I hardly ever expect things to go my way. I rarely count on good things happening to me. And analysis after analysis of data on the life orientation test suggests 2 factors. And this has led to claim sometimes that optimism and pessimism are independent constructs, that one could in principle be high on both optimism and pessimism. which again, like anxiety and depression being the same thing, I think is nonsense. You can't be optimistic and pessimistic about the same thing. You can't expect more things to happen to me, more good things to happen to me than bad, and also expect more bad things to happen to me than good. It's logically impossible. One might be optimistic about certain aspects of one's life, one's work, and pessimistic about others, about one's relationships, but with regard to a single object or with regard to orientation towards life generally, you can't be both optimistic and pessimistic. So interpretation of factor analysis as being two independent constructs, again, I think just doesn't make sense. What's going on here, I think, is exactly the phenomena we've described, where the different items are assessing different parts of the distribution. If someone says they strongly disagree that I'm always optimistic about my future, we know they're not highly optimistic, but we don't know whether they're more neutral or whether they're in fact pessimistic. They may just say, no, I think rationally about everything, so I'm not always optimistic about my future. I strongly disagree with that statement, but they might not be pessimistic. They might just try to see things as they are. So essentially the first three items are truncated from below. And then the reverse is the case with the negatively worded items. If someone says, I completely disagree with if something can go wrong for me at will, we know they're not highly pessimistic, but we don't know whether they're optimistic or whether they're kind of in the middle. And so again, the different items, the positively and the negatively worded items, are just assessing different parts of the distribution. I'm making no claim that optimism and pessimism is in fact univariate, but I'm saying even if it were, this is exactly the sort of pattern we'd expect to see. Okay, so we've seen evidence that one factor explaining the covariance structure doesn't necessarily mean that the underlying causally relevant constituents are unidimensional. Different indicators may correspond to different facets of the underlying psychosocial phenomena, which may have different causal effects on the outcome. We've also seen evidence that one factor explains the covariance structure and the shared variance is entirely consistent with, two or more factors causally affecting one another. And finally, we've seen evidence that two factors explaining the covariance structure is also entirely consistent with the underlying model generating the data be univariate. So we might kind of wonder, does this ever work? Well, I mean, I tend to think there's a reason that techniques persist, and I think in spite of these problems, factor analysis can often be revealing. So this was an example just kind of recently carried out in some of our own work at the Human Flourishing Program on meaning and purpose. But by the time we actually got to the analysis, I was kind of ready to give up on factor analysis and because of these various critiques. But we essentially were drawing on emerging consensus in psychology that meaning and purpose can be divided. There's kind of a tripartite division, what's sometimes called coherence, having an understanding of the nature of the universe, one's place in it, sometimes called meaning of life. Second, significance, finding one's own activities and engagement with the world meaningful. And then third, purpose or direction, kind of having goals that are important, things you're aiming at. We then further use distinctions in the philosophical literature to supplement this consensus in the psychological literature by dividing coherence itself, the meaning of life, into global versus individual coherence, global coherence, understanding of the universe, individual coherence, understanding of one's own identity, dividing significance into subjective versus objective significance. Subjective significance, just do I find my activities meaningful? Even if that's just stamp collecting, maybe I find it really meaningful. Versus objective, either the activity is meaningful on objective grounds or at least meaningful to the community in which one is a part. And then direction or purpose can arguably be divided into hierarchically kind of goals, just things you want to accomplish, purposes, which are broader life aims that help generate and organize goals, and then possibly a sense of life mission or vocation, a unitary notion of where one's life is heading that generates those purposes and prioritizes them. And so with the Philosopher at the Human Flourishing Program, we looked at all prior measures of meaning, collected 700 items, categorized them into these 7 categories, just purely on conceptual, not empirical grounds. Chose 3 items in each of these 7 categories, And when Noah came to analyze the data, we thought we will do the factor analysis. But I said in advance, like I don't care what the factor analysis says. I'm willing to defend these categories on conceptual grounds. But we collected data on 4,000 students at the University of British Columbia. I think many of the issues that I brought up are present here. I think there's a strong case that, for example, coherence causally affects direction and purpose, and that's what gives rise to causally affects when significant. So all these problems are, or at least some of these problems are present. So we collected the data. If you do exploratory factor analysis, again, kind of agnostic to the underlying structure, just specify 7 factors and see what the data suggest. It's not perfect, but it is pretty striking, where the first 3 items seem to correspond to the first factor, the second 3 to the second, the third 3 to the third, and so on and so forth. The bolded items are those with factor loadings above 0.3. Again, not perfect, but when I saw these, I was sort of taken aback. I didn't know what to think. And likewise, there are many other striking examples with personality, say, where the same results emerge again and again. So it's clearly picking up something important, something meaningful. So I'm going to try to synthesize the criticisms I've offered with, I think, what has been the experience of many people, that these techniques can be powerful, can be insightful. And so offer, in some sense, a reinterpretation of factor analysis, though this is, again, still thinking in progress in some sense. So again, I do think factor analysis can give insight into the covariance structure, into which indicators are more strongly correlated with one another. But we need to take into account the fact that those correlations can arise from a variety of different reasons and sources, because of conceptual relations, causal relations, assessing similar parts of distribution of the phenomena. So, I would say a reinterpretation of factor analysis is that factor analysis identifies groups of indicators with shared underlying variation that may arise from conceptual relations or causal relations or due to similar distributional coverage. And so I think factor analysis is one approach to deciding on how to group indicators based on correlations, which themselves may arise from a variety of reasons. It's a meaningful way to draw particular types of distinctions based on the strength of correlations. However, one might use other reasons or criteria for grouping indicators together, or for drawing distinctions. And this points to work, which we've got several working papers in progress. We'll be posting these probably in the next month or two. But with regard to distinctions, one might not just look at correlations, but at extreme values. In the philosophical literature, for example, conceptual distinctions are drawn if you can construct even hypothetical examples where one phenomena is present and the other is absent. If you can find someone with a high degree of sense of coherence and meaning in life, but who seems to be completely purposeless, and will say so, then those two are conceptually distinct. One could do an empirical analog, looking at the differences in these indicators and the most extreme quantiles of them. So you might take like the 2.5th quantile and the 97.5th quantile, the differences between two indicators. If those are really large, then you might say, well, we've got evidence that these are different. So it's relying less on correlations. Even if the correlations are very strong, you might still find some individuals who are quite different. Likewise, as pointed out by the first problem, we might also group indicators based on their similarities and causal effects on the outcomes we care about. Which of the indicators causally affect mortality, which don't? Or based on the effects of treatments on our outcomes. If we do a randomized exercise intervention, might they affect our anxiety items and depression items differently? And so we've been working on kind of decomposition of associations between individual indicators and outcomes into that due to a common factor versus that which is residual, which again I think can be another helpful way to group indicators together. And what might also look at both to draw distinctions and to identify similarities, you might look at the extent to which for any indicator, how much is that above or below the average across all indicators for that individual, and look at the correlation of those residuals with one another. Typically, under psychosocial assessment, all of the indicators are strongly correlated with one another. If you've got a reasonably coherent set, many times the correlations are all 0.6, 0.7, 0.8. You really can't tell what's similar and what's different. But if you look at the residuals for each individual, how much is this indicator above or below that individual's mean on average, suddenly you can see distinctions, which indicators are more strongly related to which others. And this sort of approach also is more agnostic to the number of factors or the underlying structure. So these are kind of new ways to think about how to draw distinctions, how to notice and point out similarities across indicators, different ways of grouping than just relying on factor analysis. And the second one, at least, is bringing in that causal component. So in conclusion, I'll make a few remarks on factor analysis and then a few remarks on psychosocial constructs and assessments. So with regard to factor analysis, I think this should not be viewed as the definitive method for assessing commonalities and distinctions across indicators. It is a method, but there are other ways to do this as well. I do think that assumption of a univariate structural latent variable is often just presumption, and it can and should be evaluated if that's what we think may be going on. I do think kind of causal relationships make supposedly factor discovery of dimensionality especially challenging, and I think special care is needed with negatively worded items as well. Going back to that social connectedness UCLA scale, intimate connectedness, relational connectedness, collective connectedness, if you actually look at the items, all of the intimate connectedness items are negatively worded. All of the relational connectedness items are positively worded. So I think the same phenomena is arising there. So we need to be more careful. But again, we can use factor analysis to group items concerning shared variance that may arise, again, from conceptual relations, causal relations, or similar distributional coverage. With regard to psychosocial constructs more generally, I think these are almost always multi-dimensional. That doesn't mean we can't summarize and reduce, and often an average of our indicators is still meaningful, and using causal inference theory under multiple versions of treatment, I think it even has a causal interpretation. But we should be aware of what's lost when we're doing so, about the nuances which we might be missing. Different facets of a phenomena can have different causal effects. And I do think these counterfactual decomposition methods, decomposing the association of an indicator with an outcome into that due to the common factor versus its residual effects, may hold particular promise there. So again, I think factor analysis can still be useful. I think it is sometimes incredibly powerful, but I do think it requires a more careful reinterpretation. That concludes my presentation. Thank you all for listening.